All right, let's jump right into this explainer by asking some of the absolute simplest questions about how things move. And we're going to build on that, all the way up to using real-world physics formulas. Whether you're totally new to this or just looking for a solid refresher, we're breaking down the science of motion so clearly that anyone, literally anyone, can get it.
So here's our game plan for today. 1. The frame of reference. 2. Distance versus displacement. 3. Understanding speed and velocity. 4. Uniform versus non-uniform motion. And finally, number 5, acceleration and motion formulas. Let's get to it.
Okay, think about this for a second. If you're sitting in a chair right now, you probably feel like you're completely at rest. But are you? Because depending on where you're looking from, the answer might actually surprise you. The Earth is spinning on its axis, right? And it's rocketing around the sun. So to an astronaut looking down at you from space, you are moving incredibly fast.
Which brings us to part 1, the frame of reference. This is really the perspective of movement and the foundation of all physics. The crucial takeaway here is that you literally cannot measure movement until you know exactly where you are observing it from. Motion is entirely relative. A frame of reference is really just the background or the environment that we agree to call stationary so we can measure everything else against it.
Let's use a really practical, real-world example. Imagine you're riding inside a moving bus. From your frame of reference inside that bus, the passenger sitting right next to you is perfectly still. But to someone standing outside on the sidewalk, their frame of reference is the street. So to them, you, your fellow passenger, and the entire bus are zooming by at 40 miles per hour. Neither perspective is wrong, you know? They're just using different frames of reference. So now that we know we're moving, we need to figure out exactly how far we've gone. Section 2, distance versus displacement. Right off the bat, there's a massive difference between what we call a scalar quantity and a vector quantity. A scalar, like distance, is just an amount. It just asks, how much ground did you cover? A vector, like displacement, is a bit smarter. It cares about the amount, sure, but it also demands a specific direction. Displacement essentially asks, how far are you from where you started and in what direction? Take a look at this train. It travels a long, winding, curving path through the mountains. If we check the odometer, it traveled a total distance of 750 kilometers. That's our scalar. But if we draw a perfectly straight line from the starting station to the final station, it's actually only 400 kilometers away. That 400 kilometers, plus the direction it's pointing, is our displacement. Here's a kind of fun trick to think about. If you walk all the way around a giant city block and end up right back at your front door, your distance might be a whole mile, but your displacement, exactly 0. All right, let's introduce time into the mix. Section 3, understanding speed and velocity. Basically, how fast are we going? Just like that last comparison we did, speed doesn't care at all about direction. It's a scalar. It's literally just the total distance you traveled divided by the time it took. Velocity, on the other hand, is completely direction-aware. It's a vector. Velocity is your displacement divided by time. And because displacement can be 0, like we just saw if you end up exactly where you started, your average velocity can also be 0, even if you were sprinting the entire time. Crazy, right? This football coach making U-turns on the sidelines is a perfect everyday example of why speed and velocity give us two completely different numbers. The coach is pacing back and forth, covering a total distance of 95 yards over 10 minutes. So his speed is 9.5 yards per minute. Simple enough. But because he kept turning around, his actual displacement from his starting spot is only 55 yards to the left. So his velocity is just 5.5 yards per minute to the left. See the difference? Okay, let's dive into what happens when our speed isn't perfectly steady. Section 4, uniform versus non-uniform motion. This concept is wonderfully simple. If an object is in uniform motion, it's perfectly consistent. A train locked in on a straight track at exactly 120 kilometers per hour, that's uniform. But non-uniform motion is what we experience pretty much all the time in the real world. A car constantly braking for traffic lights, speeding up, taking corners, that's non-uniform because it's covering unequal distances in equal intervals of time. Which brings us to the math. Let's tackle how to mathematically measure that exact change in speed. Section 5, acceleration and motion formulas. Acceleration is really just how quickly your velocity is changing. And remember, because it's based on velocity, acceleration is a vector quantity. This means a change in direction or a change in speed both count as acceleration. Think about it. If you're driving in a perfect circle at a steady 30 miles per hour, your speed isn't changing, but because your direction is constantly changing, you are actually constantly accelerating.
Now, please don't let these equations intimidate you. These are the constant acceleration equations. Honestly, they're just neat little logical puzzles that let us predict the future of a moving object.
Before we actually solve one, let's decode the alphabet soup so we know exactly which building blocks we're playing with here. U is our starting speed, or initial velocity. V is our final velocity. A is our acceleration. T is time, and S is displacement, the distance we've moved in a specific direction. The magic here is that if we know just 3 of these, we can always find the other 2. Let's try applying this to a real-world example. Say a motorbike is speeding up on a highway. It starts at 10 meters per second, and it accelerates at a steady rate of 1.25 meters per second until it reaches a final speed of 30 meters per second. We want to find out exactly how much time this takes. By just organically taking the variables we learned and slotting them into the very first formula, we can easily solve for t. We know our final velocity v is 30, our initial velocity u is 10, and our acceleration a is 1.25. The formula is simply final velocity equals initial velocity plus acceleration multiplied by time. So 30 equals 10 plus 1.25 times t. You just subtract the 10 from the 30 to get 20, then divide that 20 by 1.25, and boom, there we go. Basic algebra tells us it takes exactly 16 seconds for the motorbike to reach its new speed. See? Really not so scary once you break it down. Okay, now we want to know exactly how far the bike traveled during those 16 seconds. So we grab our displacement formula where s equals 1/2 of the initial velocity plus the final velocity multiplied by the time. Let's just plug those numbers right in. 1/2 of 10 plus 30 times the 16 seconds we literally just figured out.
10 plus 30 is 40. Half of 40 is 20. 20 times 16 is 320. The math works out perfectly, showing that the bike covered exactly 320 meters of displacement while getting up to speed. You just used real physics to predict an object's motion. How cool is that?
Let's do a quick recap of how we built this from the ground up today. We started with just a stationary observer to give us a frame of reference. Then we added distance and the directional vector of displacement. We introduced time to get speed and velocity. We looked at steady, uniform motion versus changing motion. And finally, we measured that rate of change with acceleration, tying the whole shebang together with simple algebra.
I'm going to leave you with this provocative thought to ponder. We know velocity changes, which gives us acceleration. But what if the acceleration itself is speeding up or slowing down? What physics concept measures the rate of change of acceleration? I'll give you a hint. It's a word you might use when you're suddenly pulled in a moving car. I really hope this explainer sparked your curiosity today, because in physics, there's always another layer of motion to uncover. Keep questioning and keep learning.